Okay, great everyone. We will now start on the lecture for, uh, in fact, this is a lecture, let me see here, lecture 5, yes. Lecture 5, Dielectric Gratings, the RCWA. So as you will have done, let me look this up, you will have done the lectures on lecture 3, which, well, all the lectures, but the most relevant ones for this lecture were certainly the last two, 3 and 4, on electromagnetic boundary conditions, and then we went to layered materials, layered media, the Bragg stack, the single layer reflection, anti-reflection coating, and also that was actually what lecture. Yeah, that must have been lecture 3. And we had the rigorous coupled wave algorithm lecture, and that was layered material as well. And that's where we had many different layers, and we looked at it not from the point of view of ray tracing, but from a full wave, coupled wave analysis. And so that was uniform layers, many of them on top of a substrate or freestanding. But each layer was homogeneous, not patterned in any way. Uh, but you can look at the overall structure, though, as being patterned, namely one layer after another. But now what we're going to do in this lecture is pattern those different layers, at least one layer, in the other direction. And so not only vertically by having different films, but within each film, within each layer, you potentially can go from one dielectric to another dielectric, or one material to another material, and back to the first material, namely having a dielectric grating structure. So we not only pattern in one direction, but we can also pattern in the other direction. So the Bragg stack lecture looked at patterning in that direction only. In this lecture we're going to do today, we're going to look at patterning only in the other direction. We'll have a substrate and superstrate, but we'll only have one pattern thin film. And then the next lecture was where we put it all together and had patterning both up and down and left to right. Now, to get ready for us to do today's lecture, we had lecture 4 in between, and that was how optical modes, electromagnetic waves, really any waves, behave in scattered media, all right? And we looked at what happens when light scatters from a single scatterer isotropically, and then what happens from scattering from two scatterers that are identical but displaced by a certain amount. And then we ramp up to looking at an array, infinite array of scatterers arrayed in a particular way. And what are the requirements for waves to experience constructive interference upon multiple scattering from that array of scatterers? And we eventually worked up to the Foucault theorem, Fourier-Foucault theorem, that says that the waves have to be of a certain type. They have to have a certain momentum or wave vector in order for that wave to experience constructive interference and be able to propagate within such an array of scatterers. And so it was really that the concept of scattering, the concept of periodic patterning, the scattering leads to the diffraction equation that we worked out last time, but then also this concept of reciprocal space and this dual lattice and the conditions on the k vector leading up to the Foucault theorem. All right. Okay. So now we're ready. We have the tools within our tool chest to effectively study and analyze dielectric gratings. All right. So let's analyze the optical properties of a simple one-dimensionally periodic all dielectric gratings. So something of this sort. All right. The structure, let me check the video to make sure, yep, we are still recording. Good. The structure is composed of 3 layers. A superstrate, material 1, and that goes all up here, the grading layer, so this layer starting at y is equal to 0, going all the way down to y is equal to minus t. And then finally the substrate, what we're calling layer 3. All right? That is semi-infinite, meaning goes to infinity, goes to minus infinity. Superstrate is also semi-infinite and means it goes to positive infinity. Okay. Now, we learned in the last lecture about the Foucault theorem, which that basically said that when there is periodicity in any layer of the structure, the fields in all the layers must include plane waves not only with the original wave vector of the wave, but also with wave vectors that are different than the original one. This is the original. Different than the original one by a multiplicative factor of capital K. And that's the usual notation used, capital K. Sometimes G, but typically it's K. Where K is associated with the period of the structure, of the spatial period, the repeat unit, according to this. Capital K is equal to 2 pi over lambda. Lambda, this is capital lambda, this isn't wavelength. But often optics books especially use capital lambda as the notation for spatial period, the repeat length. All right. Now, if we have an incident wave coming onto this grating, this is my incident K right here, K sub I. This is KXO, meaning in the x direction, the x component of this wave vector in the x direction. And if we want to express that in terms of K naught, which is your omega over C, then this is it. It's a square root of epsilon 1. Square root of epsilon 1, this is the index of refraction in 1. Index of refraction in 1. And we just denote it as square root of epsilon 1. All right? That's the relationship between dielectric constant, or index of refraction, and relative permittivity, or dielectric constant. You take the square root of epsilon to get the index of refraction. Your K naught is omega over C, and then sine of the angle of incidence. This is N K sine theta for Kx naught. Okay, so all the fields, we will expand the fields within all the regions according to, such that the plane waves have this in-plane momentum. All right, so we do that right here. Let's look first at the superstrate, then we will do the substrate, and then finally the pattern layer. So the substrate and superstrate first. So the field in the superstrate is the incident beam. Remember, we have a time dependence of e to the minus j omega t, or if you're a physicist, e to the minus I omega t. Thus, you have to have the right sign in here. When you have a plus, this represents a wave going down, and in the y direction, and this represents a wave going in the upward direction. And so we assume we have a unit amplitude wave coming down, hitting our structure, and then we're going to have a variety of waves that scatter back out, all right? Each with a particular amplitude and different amplitude, that's why, of r sub n, all right? The fact that we have a minus sign right here indicates that they are scattering upwards, all right? Now, so we have two possible polarizations that our beam can have coming down. We can have the magnetic field coming out of the paper or in the z direction. That's called the TM polarization, transverse magnetic polarization. Alternatively, we could have the wave with K coming down, and with the electric field coming out of the paper, or in the Z direction. And that is called the transverse electric, the TE polarization. All right? We're going to look at both one at a time. So, the TM polarization. If you work through Maxwell's equations, you will be able to find a relationship between your H sub Z and E sub X. And so that's what we will use these in our expansion. In our field analysis, we will use only the H of Z component and the E of X component. All right, so we're going to have to work with that. So we start our analysis here, assuming that we have an incident unit amplitude field coming down, H field coming down, a scattered number of waves coming back up, and then we use this equation and plug in H sub Z from here into here to get what the electric field then is. All right, you just simply take derivative, partial derivative with respect to y, multiply by a few constants, and you get this right here. All right, that's for the TM polarization. For the TE, we assume that E sub Z, that we have a unit amplitude beam coming down. Again, light is scattered upwards, and we use this relation from Maxwell's equations to get us H sub X in terms of your E sub Z's. All right, so you put this whole thing into this right here, take the partial with respect to y, multiply by a few constants, and this is what you get for H sub Z. All right? Now, your beta is simply this. It's always the square root of epsilon in material 1 is simply epsilon 1, kx naught, minus your in-plane momentum squared. Really, and so what this is that this is the total k right here. So if you square both sides, take this over to here, you'll get epsilon k naught squared is equal to kx squared plus beta squared. And that's really just conservation of energy. All right, so this comes from conservation of energy right here. All right, so that doesn't change at all. But Foucault's theorem, this is what we needed the whole prior lecture for, says that your k's have to be this, has to be the original wave's kx vector component plus this integer value of a multiplicative of this capital K, 2 pi over the spatial period of the structure. All right, so this is where the Fourier-Foucault theorem comes in. It's not just k naught, it's k naught plus mk, where m is an integer. Minus 100, minus 99, minus 98, all the way up to minus 1, 0, 1, 2, 3, 4, 99, 100, and so forth. It's an integer, positive or negative or 0. All right? For the substrate, it's the same type of thing, but we don't have an incident beam coming up from the substrate. Only the downward propagating scattered beams, diffracted beams. All right? So we don't have the incident beam up here. We still have the same relation once we know H sub Z, how to get E of X. We use this for TM and this for TE to go from H sub Z to E sub X. Take the partial with respect to Y, multiply by a few constants, and we get this. For TE, we do something similar to get H sub Z once we know E sub X. Again, these are downward scattered waves. You can tell that by having the positive here instead of the minus. All right. Your beta tilde, by the way, is simply this. It looks like this, but you have the epsilon 3 here because it's in layer 3. These would be the waves coming down in a variety of directions in medium 3. All right. So that's the substrate. Now, so that's all fairly easy. It's the pattern layer that gets to be more complex. And so this is actually a fairly sophisticated approach. It's straightforward, makes no approximations, makes no assumptions, and so it turns out to be very accurate. And this is what's going to help you. It's very fast as well. So it helps you when you're doing the modeling when you're doing numerical, because that can take a good long time to crunch the numbers to model a structure that looks like this. But you'll find that you'll be able to do the analysis with the MATLAB algorithm that we developed with this RCWA algorithm. You'll be able to do that within like 15 seconds, run a full wavelength scan with extreme, high degree of accuracy and confidence. All right. So the pattern layer is more difficult, and for that we have to take a step back and talk about this in great detail. Okay, and so you have the notes. I will go over it, but you can look at the video several times to cut if I go too quickly for you to get it the first time. And then we'll have our online, on our Google Chat help sessions, question and answer sessions as well. So if you miss something, don't worry about it. You can go back, listen again. If you still don't catch it, or if I leave it out, we can talk about it at some point in our next help session, which I actually want to schedule for tomorrow on Friday. So pattern layer. Now we've done the expansion of the fields in the superstrate and the substrate, and now we have to do it within this layer itself as well. Okay. So for the pattern layer, we have a bit more complicated situation. Let us look at Maxwell's equations again. So we have Maxwell's equations, as we all know and love, and we're going to look at them both for the TM polarization and the TE polarization. So first, for the TM polarization, we look at the del cross E relation, and we get this, and so we can then isolate out the partial with respect to y, partial derivative with respect to y of EX. And I pulled in the minus here for good reason. So we're actually going to be looking at minus E of x for the TM polarization. Having the minus in there, it turns out to be convenient and saves some notation, but it's not essential. But just bear with me. Let's have the minus in there, and then that is equal to this side here, but then you bring this over, to this side, and you get the partial with respect to x of E of y. All right? So we have this relation, the partial with respect to y of this value is equal to this. All right? We do the same thing with the del cross H relation. If it's TM polarized, we only have H sub z. And so this is what we have. But with TM polarization, you have both an X and Y components for electric fields. All right. So from this relation here, you get two things. You get this partial with respect to Y of H sub z equal to minus I epsilon K naught E of x. And then you can also solve for E of y is equal to this. All right. And that comes just from, again, both of those come from this equation by equating the x components for one equation, the y components for the other. All right, but now once you have this E of y, you can plug that back into this right here, all right? Therefore, eliminating E of y. And so you will have only two equations that only depend on h of z and E of x, not E of y. So h of z and E of x. And on this side, the left-hand sides, you see they're both partials with respect to y of h of z and minus E of x. And on the right-hand side, you see that this only depends on minus E of x for the first equation, h of z for the second equation. All right? All right. Now, we're going to make a guess, an assumption, and then you work through the calculations to see if we encounter any nonsense results that would say that our assumption cannot possibly be correct. we assume that h sub z and minus e sub x have a spatially y dependence of this. All right, that is a plane wave, not only in the x direction but also in the y direction, and that's a pretty safe assumption. So, but let's see where it leads us. So both of these things up here, as they stood, had both an x dependence and a y dependence. This, and this. But now we're going to separate out the y dependence like this. All right. And we then can stack one function on top of the other in a matrix type of thing. And then we have this right here. Okay. But we don't have to do that right now if you don't want. Okay. But if we were to do that, we could write a big matrix relation, a calculus-based matrix relation, where we take, see, on this side here, we have partial derivative with y, partial derivative with x. So if we have a two-row column matrix, of these two things here, this left-hand side is the partial with respect to y of this. And that's what we have right here. All right. But then we have to, then the right-hand side, you have to construct this matrix here. And because the partial with respect to y of h of z only depends on e of x, and the partial with respect to v of x only depends on h of z, you have zeros here and here, and you have those two operators here and here. All right, and so this is our first stab at it. Now, what we can do here is take this y dependence right here, take the partial with respect to y, then cancel on both sides this y dependence, and you will have I tau phi is equal to L, this matrix, times phi. All right. So far, so good. Nothing all that difficult. Okay. Now we go back to the Fourier-Floucault expansion. We said all of these waves, H and E, they not only have to have a y dependence, we assume they have a y dependence of this, but the Foucault-Fourier expansion theorem says that they have to have an x dependent. That's a combination of plane waves, where the kx values has to be different from the initial kx value of the incident beam by an integer multiple of k, capital K, which is 2 pi over capital lambda again. So h of z, e of x for the Tm polarization, e of x, e of z, h of x for the TE polarization, all of those fields have to have a wave expansion according to this. This is the Floucault theorem. All right. Now, Fourier analysis says that for any geometric feature, you should be able to expand it according to Fourier's theorem, such that epsilon, and we'll also be using 1 over epsilon, have to have an expansion according to this. So the difference between this expansion and this expansion, between fields and geometric structures, materials, is that you just simply don't have the kx naught in here as you do in this expansion. All right, that's the difference between Fourier's expansion and Foucault's expansion. All right. Now, we have these coefficients out here in front. We're going to make a matrix of this such that we have the h coefficients in front of their respective plane waves. That represents for the Tm polarization the h sub z, and then we'll have the e of minus e of x coefficients for the electric field expansions. All right. Since we want to get rid of this minus sign, we just call this minus e of x coefficient in front of here a chi. And you'll see this in the MATLAB code. I use chi from here on out. All right. So far, so good. All right, so we're going to now put these things into this equation to this equation here, this equation here. And we look at it one equation at a time, because really these things are two different equations, two separate equations. This equation and this equation with the I, here we do the d over dy, so we have I tau. That's where this comes from, I tau. So this actually is a matrix equation which includes within it two equations. And the first equation gives us this. All right. If you expand this, we get I tau, and then I tau times we get I tau times phi, which is my h sub z. And this is my h sub z right here now, expanded with this x dependence expanded according to Foucault's theorem. That's equal to the right-hand side. I k naught. Now you have to do both the expansion of epsilon and the fields together. All right, so we will have two summations here. One for the expansion of epsilon according to this equation here, and one according to the Foucault theorem for E according to this equation. All right, and so you'll have e to the I n capital K from this expansion, and then from the field expansion you'll have e to the I kxp for the field expansion. When you add those two things together, you'll have k naught plus n capital K plus p capital K. Or take out the capital K, you'll have kx naught plus the quantity m plus p times k. All right, and then you write it still in this form, and with the m and p in there in front of the capital K, then it becomes kx comma p plus n. And so that's what we have. All right. Now, when you equate the two plane waves, you have to find the values that match. So m has to be equal to p plus n. All right. Or m has to be equal to p plus n. N. All right. So therefore, you can solve for n has to be equal to m minus p. All right. So this double expansion goes down to 1, and then you're able to express this in terms of this right here. All right, where n now is changed over to m minus p, and you are summing over. You're summing over p here. That should be a p. You got to figure out how to make notes of this. So this should be p. All right. Now, this whole thing here can now be turned into a matrix equation where you're multiplying two things together. One matrix versus times a column matrix. All right. I've introduced the L's here to denote that we're going to have eventually an eigenvector-eigenvalue problem. And you know that for an n-dimensional matrix, you're going to have n eigenvectors and eigenvalues. And that L denotes which eigenvector-eigenvalue we're working with. And we'll use that later on. This is called, when you make a matrix out of these things, where the MP component or element of this matrix is equal to the Fourier component, the m minus p element of the Fourier component expansion. This is called the Toeplitz matrix. All right. So we define a square matrix called the Toeplitz matrix, and then we have a value. This is going to be the eigenvalue, as we'll see here in a moment. HL is equal to K, Toeplitz matrix of epsilon, chi, sub L. All right. So that's that equation. Now we work with the second equation. The second equation that comes from this row. All right, and we do the same thing. A little bit longer. We have some derivatives in there. But once you get down to it, you get this right here. And again, you have another Toeplitz matrix right here. So so we have sum over S, and so we have kx times eta Toeplitz times kx again times the expansion coefficients plus k naught h sub n. All right, putting this in matrix notation, this is what we have. And thus, we now have these two equations. We have this, and we have this. All right? So we are now going to combine these two things where we put all the h sub l's on top of all the chi sub l's to make this column matrix phi. So we have on the left-hand side tau times chi, tau times hl, and so when we're combining those, putting the h and the chi on top of each other to make a big column matrix, we have just tau times that column matrix. On the left-hand side, on the right-hand side, we combine this, combine this right here. And that goes into the first row, second column, because we're multiplying against chi. And so first row, second column, we have that right there. Whereas this will go into the second row, first column, okay, because it's this set of coefficients. So second row, first column for that. All right, and now we have what looks to be an eigenvector-eigenvalue equation. We have a matrix times a column vector is equal to a constant times that column vector. That is the definition of an eigenvector-eigenvalue equation. All right? And so in MATLAB, we can put in simply saying for the MATLAB function EIG, and then we put into the parentheses there, this matrix M, Tm, and out will come the eigenvectors and eigenvalues, and I'll show you that in a moment. So we will get a set of these phi's. Those phi's go back into this to give us the x dependence of the fields, of the H and E fields in the layers. And remember, we already have the y dependence of the fields by this. All right, and now we have everything. We have the x dependence, the y dependence, and we have all the parameters that tell us how those dependencies behave. We have the tau for the y dependence, and we have the kx's for the x dependence. So we have everything we need. So h sub z in general is given by this right here. So it's a combination of all these different modes where we've taken all the different modes with their y dependence and x dependence, and for each of the different eigenvectors, you might have different contributions of the fields from those different modes. And these coefficients A sub L represent that, the different contributions of each one of those eigenmodes. All right? So really, these are the unknown expansion coefficients of those h sub z eigenmodes. Same thing with minus e of x. You have the expansion coefficients times the y and x dependence, and then this is necessary to tell you the composition of each individual eigenmode themselves. All right. So that's what we have for the TM polarization. The TE polarization is very, very similar. We start with Maxwell's equations. We get two equations for partial with respect to y. We work with we have this. We're also going to want d over dy, the partial with respect to y, of h of x. We want to substitute something in here for h of y. We get that from the second Maxwell's equations right here. This then will go into here, and we can have two then equations just like we have before. All right, and this is what we have. Again, we let the fields have a y dependence of this. We can combine these two functions into a matrix function like this, one on top of the other. And then we can express that equation taking the partial with respect to y on the left-hand side to get this right here. And we and this is, again, the matrix of a matrix of functions, a matrix of operators. All right? Just like we did before, we do a Fourier-Floucault expansion of the fields, and they will, and this will be a big column matrix. And we stack those coefficients, electric fields above magnetic fields. And thus we can now work with the two equations that this big matrix equation provides. So we separate that out, working with one equation at a time, and we get this equation here after working with the first equation that the matrix function gives us, matrix of functions, and then we get this second equation. All right. We can then combine that, as we did in the TM polarization, to get this right here. And again, this is a eigenvector, eigenvalue problem. Just like within the TM polarization, we can write E sub z and h of x as an expansion of these eigenmodes here. Each eigenmode is given by this after we do the sum over m. But we compose these fields as a combination of these eigenmodes, and that's what the A of L tells you the individual strengths of the different eigenmodes. All right. So we have E sub z and h of x. So that's it, because going through this, what we will have found is that we will get this through our Fourier-Floucault. We know it's kx naught plus m capital K, so we know those values. This we will have found out by solving for the eigenvalues of this equation. And we will know these because this will come out of the solution to the eigenvector eigenvalue equation. You'll see that in the MATLAB code. So the only thing we don't have at this point are these expansion coefficients. The expansion coefficients, the coefficients in front of our eigenmodes. So we don't have the A sub L's. All right. And that's where we're going to now need to look at the boundary conditions when the field goes from the superstrate, hits that interface between the superstrate and the pattern layer, layer 2, and then the fields at the pattern layer substrate interface. So using the boundary conditions of continuity of the tangential field components, and E sub z, h of x are the tangential field components for the TE polarization. H of z and E of x are the tangential field components for the TM polarization. All right. So we'll have everything. So we will need to do those boundary conditions. But before we do that, we are first going to look at how to. One of the things we need to construct this matrix, and obviously the things we need is we need the Toeplitz matrix for epsilon, for that, and the Toeplitz matrix for eta, for the TM polarization. So, and remember what the Toeplitz matrix are. Toeplitz matrix are given by this. So we need to know the Fourier components of epsilon and eta. So let's do that next, the Fourier components. So this middle pattern layer will have two dielectrics within one period going from x is equal to 0 to x is equal to capital lambda. First material, The first index says that this is layer 2. Second index is for the material. So this is layer 2, material 1, layer 2, material 2. And material 1 goes from 0 to W. Material 2 goes from W to capital lambda. All right? Epsilon has to be expressed as this. We used this before. And now we're going to find this by multiplying both sides by e to the minus is capital Kx and integrating over one period and having 1 over capital lambda out in front. All right? When you do this integral on this side right here, you get epsilon s, you get the s component of epsilon. When you do it on this side, you have to put epsilon as a function of x on this side. In between 0 and w, it's epsilon 2, 1. It's epsilon 2, 1 in between 0 and w. In between w and capital lambda, it is epsilon 2, 2. So it's epsilon 2, 2. When you do these integrals, the epsilon s just turns into this. You simplify it a little bit further, and you get this right here. At least when s is not equal to 0. If s is equal to 0, you can go straight back anywhere here. You can go back to here, for example. This is still epsilon s, but this is when 0. And you have to go back, and you'll see that epsilon 0, when s is equal to 0, is just simply the average. Well, not quite the average, the weighted average, according to how much space material 1 occupies relative to that of material 2. So epsilon 0 is this. When s is not 0, it's given by this right there. And the same with your a's. All right. So then we can go to the Toeplitz matrix construction. And so we do that. So let's read through this. If we expand the field in x-dependent Fourier components of this with m is equal to minus n to n. Okay, I know, I remember why I did this. You will have, if you add up the number of modes here, you get 2 times n plus 1 components. All right, when you go from minus n to n. The Toeplitz matrix, as it turns out, when you do this sort of thing, the Toeplitz matrix then will be given by this, where you go the minus n, minus n, minus n, minus n plus 1, and you keep increasing the column index by 1 until you get to minus n, n. All right? When you go along the row, you don't increase the column index, you increase by 1, you increase the row index by 1. So minus n plus 1, minus n plus 2, minus n, all the way up until you get to n, comma, minus n. All right? So that's how you do it. Okay? So each one of these components, remember what the Toeplitz matrix is. It's the Fourier component of this minus this. All right? So putting these in terms of the Fourier components, you have epsilon zeros along the diagonal, all right? Because it's always the same. N minus n is 0. N plus 2 minus n plus 2 is 0. So all along the diagonal is 0. But if you look at here and here, you get epsilon minus 2n, epsilon plus 2n. So, and then you get everything in between. You get from minus 2n all the way up to, from minus 2n all the way up to 2n and everything in between. Not just minus n to n. You go all the way over to minus 2n, to positive 2n. So you're going to need a lot more components of epsilon than you do for the fields themselves. So that'll be important in the MATLAB when we implement this in MATLAB. Thus, if we expand the fields in 2n Fourier components, we need 4n plus 1 Fourier components of epsilon and eta. All right? Okay, so that's that. All right? So we're going to use that fact in the MATLAB program. So, check if the video's still going. Yes, we're at 45 minutes. Okay, just a bit longer. Let's look for a second at unpatterned layers. If we have an unpatterned layer, then the only Fourier component of epsilon we have is a zeroth component, and the rest are zero, but not the zero component. The zero component for an unpatterned layer, meaning maybe for the superstrate and substrate. We only get a zero, n is equal to 0 component. All right, and so this Toeplitz matrix and this Toeplitz matrix turns into single values. All right, and so then that's much easier. We can then solve. We can separate this out into the two equations, all right, and get this equation and this equation. And then we can combine these two equations into one, getting this. And then we can solve just analytically, really easily, what this tau is, this eigenvalue for the simplified problem of fields within an unpatterned material is. And you see you get the expected results, all right? This should be expected. Remember, this is the y-dependence parameter. You should see why this should be expected, and if you don't, you should review it until the point where it does become obvious why this is what it needs to be. And then you can put this back into any one of these equations, like this one right here, and solve for minus e of x. And so you get this relation between h of z and e of x for the moment. All right. For the TM polarization, similarly, you get rid of Toeplitz matrices, and they go down to single values for the epsilons, and you have these two equations. You solve for tau, you get the expected result. You can solve for h of x in terms of e sub z. All right, that's just a reality check when you look at this for a simplified situation of unpatterned. All right, so now we are in a position to do the final step, meaning we have the field expansions in the superstrate and substrate and the patterned middle layer, and now we have to glue them together, all right, and apply the initial condition, and then look to see all the fields that are excited. To do that, we use boundary conditions. We look at boundary conditions at the first interface, superstrate to medium 2 pattern layer at y is equal to 0, and then the boundary conditions at y is equal to minus t between the pattern layer and the substrate. So TM polarization first, right at superstrate pattern layer interface, y is equal to 0. Setting y is equal to 0 for h sub z, all the y dependence drops out, and we get this right here. Putting all the unknowns on the left-hand side and all the knowns on the other side, we get this equation right here. All right. E of x, going back to where we had E of x in the notes, and evaluating it at y is equal to 0, we get this relation here. Equating the proper kx terms yields this equation here. This can be taking the unknowns over to the left-hand side, so this has to go over to the left-hand side. Knowns over to the right-hand side. You get this right here. All right. So we get those two equations. Continuity of h of z minus e of x at y is equal to 0. We now have to do it for the second interface at y is equal to minus t. All right. We have the hz fields in the pattern layer, but now we're down in the y by minus t. So we have this term in there that represents the y dependence of the field after we go from 0 to minus t. And then we have the transmitted beams on this side, magnetic fields. All right. These are unknowns too, so we take that over to this side and equate the proper plane wave components, and we get this equation right here. for minus c of x, we start with this equation. Oh, and by the way, we're letting this be called gamma. So that, and we for minus c of x, we get this equation right here. All right. So our unknowns are what? Our unknowns are r, a, and t. So we're going to make a big column matrix of our unknowns. R, all the r's, from minus n to capital N. All the a sub l's, which the L, there's 4n plus 2 of these unknowns. All right, so that's all stacked up here in the middle. And then the 2n plus 1 unknown transmission coefficients. All right, for the 2n plus 1 possible scattered waves coming out of the substrate. Likewise, these are the 2n plus 1 possible diffracted waves in the superstrate. We have to find the relative strengths of each one of those possible diffracted waves. That's what we're going to do. All right. So then we have the right-hand sides. This and this and this and this. All right. And we combine, and that is our known, our initial condition column matrix. 0, and then we, for the 0th order incoming wave coming down, we have a minus 1. It's unit amplitude, but we've taken it over to the other side, and that's why we need the minus sign. Other side of the equation. All right. And likewise, so the rest of the incident beam coming down components, it's only a 0th order incident beam coming down. And likewise, for the electric field, we have a 0th order incoming electric field, having non-zero value. Everything else is 0. All right, everything else is 0. And then we collect and make the big coupling matrix from these 4 equations. So we have, we're going to have a matrix that combines all the h's, and then we have 0. There's no t in here. There's no t in here, so we'll have 0 for t. So that's, we should have for the coupling matrix 1, a matrix with the h's and a 0. All right, and then that's for the magnetic field. For the electric field, we'll have a minus beta epsilon k naught minus chi matrix and 0. Minus beta epsilon k naught minus chi matrix 0. All right. So these are the H boundary condition, EX boundary condition. We need the H boundary for the superstrate to layer 2 interface. Now we need the layer 2 substrate interface, H of Z, E sub X boundary condition. All right, and those come from this equation and this equation. We'll have H gamma, and then minus 1. Along with the 0, H gamma minus 1, and chi 0, chi gamma minus beta over k naught epsilon. 0 for the r's. Chi gamma minus beta tilde epsilon 3 over k naught. All right. So we have now this big relation here. All right, where we have this matrix times the unknowns that we're trying to solve for is equal to the incident wave condition matrix. So we take the inverse of m, multiply both sides, and then we're able to solve for the unknown expansion coefficients. All right, and that's it. And I'll show you how to implement that in MATLAB. And you do the same thing for the TE. Where are we at in terms of time? All right, it's getting to be a long lecture. You do the same thing with TEs. You have to evaluate the boundary conditions at y is equal to 0 and at y is equal to minus t. All right. So the y is equal to 0 boundary condition, continuity of the E sub z gives you this relation. Continuity of h sub x gives you this relation. At the bottom boundary condition, at y is equal to minus t, continuity of electric field gives you this. Continuity of tangential magnetic field gives you this. Unknown coefficients are the same as before. Incident wave condition very similar, but you don't have the epsilon down here for the t E polarization. And you have the coupling matrix. The only difference between the TE and TM are you don't have the epsilon here and the epsilon there, and but you still solve it the same way. All right. So now we are ready to implement this into MATLAB. So let us look at now MATLAB. So let's take this away. Let me see if I can do this. Minus. Yes. Add. Window capture. All right, bear with me. There. Okay. Put this back up there. All right. Here's the MATLAB code. So let me go to that right here. All right. Let's see if it's doing it. Oh, good. All right. MATLAB code. How many lines is it? It is 324 lines. Not all that long. Define the wavelength. Define the period of the grating. The number of waves in our expansion. This is the same capital N as in the theory, as in the notes. We create two figures. We define the structure. All right. The thickness of the superstrate doesn't matter, so we set that to 0. It's not used. Likewise, the superstrate, the substrate thickness isn't used either. We set that to 0. But we define the epsilon. This is epsilon 1. This is epsilon 3. And in the grating layer, we have layer 2. And then we have material 1, material 2. All right? And so material 1 will be like silicon, having dielectric constant of 13.7. And it'll be, I have a half micron wide. The period right now I have is 1 micron. Material 2 is just simple, epsilon is 1, so it's probably vacuum. And then I have the width of that being equal to the period minus the width of this. So that this is 1 minus 0.5, or this also is 0.5 at the moment. All right? Now I start the code. I say I want 1,000 points in my wavelength scan. My wavelength scan going from min to max. I do a whole bunch of predefinitions so I don't get any warnings. This might be the very first MATLAB code where I have a green light here. So I predefine everything. This is my capital K in the theory, my epsilon 1. Instead of using this whole big long thing, I just want to use something shorter. So I just redefine that. Same for the epsilon 3. Okay, I first had to find the Toeplitz matrix. To find the Toeplitz matrix, I had to find the Fourier components. And I have to go, this is where I'm going, from minus 2n to 2n, because I have to go to twice the number of components as the field, as required by the field. So I have, instead of going from minus n to capital N, I have to go from minus 2n to positive 2n. And so I then will simply put in the equations for epsilon component here and eta component here. So this is when S in the notes, when I said S is not 0, I use this. When I'm looking at S is equal to 0, I use the weighted average of the two epsilons, and that's in this, because this is, C and T is my S in the notes for finding the Fourier components of epsilon and eta. All right. So then I'll have all those. And so then I just simply have to create that big, long Toeplitz matrix. So if I were to add that back in, I could go back. Add. Window capture. Window capture 2. Okay. Let's see. Yeah. So now I want to construct this matrix here. And so that is what I'm doing. right here, right here, right here. Okay. And now, once I have the Toeplitz matrix, that doesn't depend on wavelength, so I can do that all outside of the wavelength scan. Wavelength scan starts right there, and now I start the wavelength scan, and I first find my betas for the superstrate, betas for the substrate, and my kx. This is where Foucault's theorem comes in. This is my kx. This is my CNT in this for loop is my M in the notes. All right. So I found KX, my beta tilde. Beta for superstrate, beta for the substrate. And now I'm just simply going to now be solving for I'm going to be now solving for oh, I think I did it before. These coupling matrices. These coupling matrices here. All right, so you'll see that that's what I'm doing now. Now that I have my Toeplitz matrices, I will now solve for these matrices. So that's what I'm doing right here. I'm putting together those big coupling matrix first for the TM polarization. All right, and I find the eigenvalue, eigenvector here, and I find the eigenvector is given by this. The eigenvalue is given by here. All right. Now remember, these eigenvector ones are stacked, hz minus e sub x. So I want to separate those two things out. So that's what I do right here. I grab, in this case, just the h portion of my unknown column vector. And in this one, I just grab the underlying minus x coefficients of my unknown column matrix. All right. Those gamma functions I have right here. I define right there, and that's that. So then I have switching back to the notes. I then have M. I then will have solved for my eigenvalues and my eigenvectors. And I will have also have, at this point, defined these gamma functions. All right. So now we're ready to create these big matrices right here for the boundary condition things. So let's go ahead and do that. So now we're able to, okay, first I do it for the TE to find the eigenvectors, eigenvalues in layer 2. But so here is where I start making those big coupling equations for the boundary conditions, all the different m's. So we have 1 minus h, 0 for the top row. And so we look at that, 1 minus h, 0 for the top row. And then we'll have minus beta over epsilon k naught minus x minus chi 0. And that's what we have here. We starting off, we have minus beta over minus epsilon k naught minus chi 0. All right, so we're making that matrix, and then we're putting it all together. We're doing the incident beam conditions right here and here, and then we solve for the unknowns, and these are our unknowns, my r's, my t's, my fields in the pattern layer. And then I grab the appropriate one for the reflectance and grab the appropriate one for the zeroth order transmission. Zeroth order reflection, right here, zeroth order transmission. And then I take the modulus squared of that of lowercase r modulus squared of t multiplied by some values to get the reflectance and the transmittance. I find also for you so the diffraction when that occurs, as well as the total energy by all the beams. And then I plot out these reflections and refractions. Do the same thing for the TE, for the boundary condition matrix equations. And then I finally plot it out in these lines right here, lines 285 to 324. All right? Now, and then when you run it, give it a second. So for 1,000 data wavelength points, we get 2 graphs. Let me pull up on the video, another screen capture. Figure 2. Okay, and this will come up. So we plot out the reflectance. The reflectance in red, the transmittance in blue, and then we will get the diffracted orders. You will see it's 0, 0, 0 at a high wavelength, but as soon as that wavelength reaches the effective period of the structure, capital lambda, you'll see it go from being 0 on the high wavelength side to non-zero. From from 0 on the high wavelength side to non-zero. So this is our first diffraction beam coming in. So this would be light coming straight down. As we scan from higher wavelengths to lower wavelengths, you have no diffraction at all, and so light would only come right back up as a reflected beam. But once you get down to this wavelength, a little bit below the period of 1 micron, you'll have the first diffracted beams that shoot off to the side. All right? And so this represents the fact that you have energy being delivered to those 2 other diffracted beams. Okay. So you'll have to go through the notes, but we built upon the last lecture where we developed the Foucault theorem, which it showed you how you had to okay, why is this not working? There. How you had to expand the fields in patterned materials and periodic materials. And the fact is, you had to expand them go back here. In this way right here. So the whole prior lecture was showing you the fact that the fields have to have an x dependence of this. And then we could develop the very accurate and useful, as it turns out, rigorous coupled plane wave approximation. I've used this for the past 20 years, actually, as a go-to thing before I go into finite element, the finite difference time domain, with any of the high power HPC systems to do modeling. I go to and look at RCWA because generally I have no doubt in the accuracy and is very fast. And so even though the math is a little cumbersome and that now you have the algorithm in MATLAB, it's extraordinarily convenient, easy to implement, and it's a very first round type of modeling technique to get you some preliminary data. Okay? Downfalls of this method is that it can't do any complications to perfect periodicity. Like what if you have surface roughness here, or not straight sidewall profiles? It turns out to be much more difficult, and in fact almost impossible to use a rigorous coupled plane wave algorithm. Not quite impossible. There are techniques to do it, where you have slants and sidewalls. In fact, I'll show you a really interesting one later on, where we can do curved interfaces with the rigorous coupled plane wave. But this is the simplest one. It's fairly simple. Um, but saying that, even though it's simple, there's what, how many pages? 25 pages worth of notes to implement this thing. But it's all very straightforward mathematics. Okay? And so I will put up the MATLAB code, and I'll have you investigate different diffraction gratings, optimizing diffraction gratings for particular applications. Okay, and then we'll build on that. The next lecture is where we will put our pattern layer in between two Bragg stacks and figure out why we would want to do that. What does a pattern dielectric grating in between two Bragg stacks, what useful thing does that do for us? It turns out it's something that is extraordinarily useful, and we've just received, we received a good number of grants to develop a device that has the performance that we'll cover in the next lecture. Okay, so take care.